Coming up on Evolve the Earth, we explore with Professor Scott Hildreth and discuss how physics and astronomy is part of our everyday lives. On this two-part episode, we take our conversation to outer space and beyond. All that plus more on Evolve the Earth. Hello, and welcome to another episode of Evolve the Earth. And today we have a special guest, Professor Scott Hildreth. How are you doing today, sir?
Thanks, Alan. It's really fun to be here with you. Appreciate the invitation.
I appreciate it as well. How did you actually get into physics and astronomy?
Yeah, I think it's such an interesting question also for Chabot. When you ask all of our students, do they know what they want to do? And when I was a student in college starting out, I was a math major. I loved math and science, but I had no idea what kinds of jobs might be available. I enjoyed learning about astronomy, but I never ever thought that that would be a career.
Okay.
And my mom was an artist and my dad was a writer, and so neither of them were strong in mathematics or science, and they thought maybe the babies got mixed up in the hospital. I love that stuff, and I went to the University of California, Davis as a math major because I grew up in Berkeley and I didn't want to go to Berkeley because that was my backyard.
Okay.
So lots of our students come to us at Chabot, we're not necessarily sure what they might want to do or where they might want to go. I was very much the same. I got very lucky. I went from Davis to the University of Edinburgh in Scotland. The University of California had this great program where you can spend a year abroad learning and still pay California tuition. You didn't have to pay foreign student tuition. And so for me, I was a chance to go learn in Scotland, learn mathematics and physics. But there was an opportunity to walk up the hill to the observatory that Edinburgh had. And it was a fully functional observatory. And I did it more as, oh, that's kind of an interesting thing. I wonder what's going on. And I met a UCLA professor who was over there on sabbatical, who had written books I'd actually read before I had gone. George Abell was his name. And he was so kind as to literally delay the start of his class he was teaching so I could walk up the hill every afternoon after my math and physics classes. Given that chance, after a year of working there, he was kind enough, and I was lucky enough to get some letters of recommendation to go to graduate school. And I ended up going to Berkeley, as it turned out, for family reasons. I stayed in Berkeley. There was an opportunity to go to Princeton, where Einstein was, and a number of other folks. There was an opportunity to go to Harvard and Chicago and Caltech, the best schools. I was very, very lucky. I ended up at Berkeley. I went to grad school in astrophysics and took also engineering classes. Radio telescopes are big. Radio antennas, so learning a little bit about astronomy in terms of radio telescopes also meant learning a little bit about electronics. I was able to do that and then go to work for IBM as an engineer, staying near in the Bay Area. I had a great chance to work with IBM to make computers talk to each other before the internet. So this is, in the internet world, everybody talks the same language.
What year was this, by the way?
This was probably 1980, right? So prior to the internet getting around, if you were one kind of computer, like an Apple, and somebody else was another kind of computer, like an IBM, they wouldn't talk to each other. One was talking Mandarin, one was talking Russian. And so making IBM's computers themselves talk to each other was a neat job.
It was like a universal language?
It was. Well, you had to end up programming both computers and all the hardware in between. And so the chance to do that was fantastic. I worked all around the country helping to diagnose networking problems. Became a manager, then went from IBM to a startup and worked in a startup for a couple of years, traveled everywhere around the world. Although it sounds sexy and it sounds attractive, a hotel, cab, business meeting, cab, hotel, airport, wherever you are, a lot of us lost after 2 years. I got a chance to teach Chabot a summer class just as a break from traveling. I had so much fun. I stayed, and that was 35 years ago.
I know you said you went all around the world. What was your top 3 places that you visited?
Oh golly, that would be too hard to say.
Okay. What stands out the most?
Regardless of where it is, living someplace, whether it was Scotland or I also lived in New Zealand or visiting anywhere in Europe, just going somewhere else, I think, is such a broadening experience for folks. I had so much fun, but you end up seeing that other people elsewhere are just the same as us. They are just as interested in learning. They're just as interested in doing the very best they can. They want their kids to survive and succeed. They go to supermarkets like we do. They're no different. There aren't differences that we create either politically or sociologically. They're just humans, and I think I love that sense of being on the other side of the world in New Zealand and finding people talking about the same kinds of stuff we talk about. Going to to Alaska and finding people from the Inuit, the Eskimo, and they're talking about the same things we are. We are one people, maybe scattered around the globe a wee bit, but we're one people, and we have these same kinds of interests. It really does transcend to this topic because science is something everybody shares. And
it's
the sky and universal, right? Everybody shares astronomy. No, it's not restricted to one group, one person, one country. Whether you have hair or not, it doesn't matter. Everybody can enjoy it.
We're hearing a lot about quantum computing today, and it's based on quantum entanglement. Can you help us understand what it means?
Yeah, it's so much fun as a physics professor trying to take what's going on now today in the world and abstract it and help our students kind of get a sense of it. And so you look at quantum computing, and IBM, the company that I worked for almost 10 years, is leading the world now in actually selling quantum computers. So this isn't just theory, this isn't just an idea. There are companies making quantum computers, selling them, and we are using quantum computers to improve our understanding in health and diagnoses of disease and results. We're using quantum computing in all kinds of ways. This technology that is capturing images wouldn't work without understanding quantum computing at some level, because some of the plasma technologies that we've got for the monitors and the capturing technologies of the chips are based on that. So this isn't science fiction.
No, not
and
no more.
Okay, based on this idea that a traditional computer would understand either a 1 or a 0, it has no difference. In other words, it's either a 1 and a 1 or it's a 0 or a 0, and there's never in between. And it goes to this idea of binary digits or a bit, and there's no way anything could be other than a 0 or a 1. So a quantum computer says it's both a 0 and a 1 until you look at it. And you might think, well, that doesn't give you much, but I have a small demo, so we're going to try that and see whether this works.
Small demo.
Here is a black ping pong ball. I'm going to put it in a box. And nothing up my sleeve. I have an identical box with a white ping pong ball. Now, if I shake these around and move them around and I forget which hand has which ball and hand it to you, open it. What color ball is it?
I got the white one.
What color then must be in here?
The black one.
So that's what Einstein said. In 1935, Einstein said that there is a property that this ball has and the ball you have that is inherent in the ball. And the fact that you opening yours up identified instantly that this had to be the black ball. That's a bit. Your bit, my bit, no difference. So now we're going to change the experiment up. And I have 2 more balls. So you have a black and a white ball in your box. I have a black and white ball in my box.
I can't tell no more.
Can you see what's going to happen?
I can't.
We're going to mix them up. And you're going to open your box, and I'm going to open my box. Now, don't tell me what you're going to pull out. Pull it out randomly. Don't even look. Pull it out randomly. This is live TV. What did you get?
Oh, we got a complete opposite.
So here's what quantum entanglement means. Every time you pulled out a white ball, I would pull out a white ball. Every time you pull out a black ball, I would pull out a black ball. Now, you would think, you would think that if for that to happen, there had to have been some way that the black ball coming out into your hand translated over here to the black ball coming out of my hand. In other words, they were entangled. Here's the best part. Einstein said, 1935, in a famous paper, the Einstein-Podolsky, the EPR paper, Rosen, the Einstein-Podolsky-Rosen paper. Einstein said that the information that you pulled out a black ball and then I would pull out a black ball had to travel this distance. But nothing can travel faster than light. What the question was is, how did your pulling the black ball out cause this black ball to know that's the one to be pulled out? Einstein said it would have violated relativity. The information would have had to have gone this far faster than light, and therefore it wouldn't be possible. And he rejected the entire idea as not being as deterministic as the physics that we had inherited for years. The idea is, this is definitely a white ball, this is definitely a black ball. The two aren't both, aren't neither, they are one individual objects. That's a Newton, that's an old physics view. Here's our new view. Our new view, an entangled particle, is both. It is black and white. It's black and white in your box, it's black and white in my box. And until you look at it, then it's one or the other, but not till then. And so you'd argue, well, what good is that? These boxes are called qubits. They're quantum bits. They are both a 1 and a 0, and best of all, shaking them up, I could be light years away from you and they still remember, you pull out black, I'll pull out black.
Wow.
Farther than the speed of light could get in the time frame. So this means an entangled photon has information that the universe should not allow to go as fast as it does.
Sure.
And it's changing our way to see the world. We thought of space as this fixed distance. I could bring a ruler and say, oh, you and I are a meter apart.
Right.
And that indeed, what Einstein with general relativity had this idea of space as being this fabric in space and time, and it's bent by the presence of matter. But it's still physically a distance. Right. And entanglement is saying, maybe space isn't what we think, because somehow, even if I was light years away, you pull the black ball out, I pull the black ball out.
Right.
How would it know?
How does it know?
So you might argue, okay, well, what does that give you as a quantum computer? Well, a quantum computer would say, and a classic example would be, let's say that I have a student at Chabot, and they want to take in a year of classes. Maybe they're going to be a full-time student, they're going to take 4 classes each term, including summer. Right. So 12 classes a year, and they want to know the sequence of what class they take at what time, at what semester to be able to graduate.
Okay, yeah.
So that's a computing problem. They need to know what classes are offered, they need to know when they're offered, they need to know what semester they offer, they need to know whether they're, in one side of the campus or the other, so that if one ends at 10 o'clock, they could make it to the 10:05 one start. I mean, there's a lot of factors, right?
Yeah, a lot of factors.
Program that computer, you would be able to figure out a program that'll get you the best schedule as a student.
Wow.
Right? But it's probably going to take that computer with all the inputs minutes to figure out all the possibilities. It's like a chess game, right? A chess game where you have all these possible, you could take math first, you could take English second. Sure. You could take art. Yeah. Oh, wait a minute, maybe you could better take physics. So imagine that combination of variables.
Right.
A quantum computer would solve it instantly.
That is just amazing.
Instantly.
That's just
It'll
so
solve
fast.
it thousands of times faster. And here's why. Because quantum computers aren't so simple as just 2 qubits. I can entangle lots of qubits. So I have 2 more balls and 2 more balls and other ones. So now, if you could imagine this with 7, 8, 10, 30, 40 qubits length. Think of the degrees of freedom that I could then solve a problem with. It isn't just one student figuring out their optimal schedule, it's every student at Chabot figuring out their optimal schedule. Every student. Instantly.
Wow, instantly.
And so if you could imagine harnessing the power of the fact that each of the qubits is everything still in this box until I go find it. It is possible. I could have every possible input schedule in this box all at once. And the power of quantum computing is it's changing our way both to program, but also to change our way of solving problems and seeing how we can solve problems in ways that our traditional linear computing systems that we built on for years and years would solve. There's a neat way when you're a computer scientist of learning how to kind of create a graphic of how a program is written. One of the actual things you could do and students can do is they can go to the IBM virtual computer and a quantum computer for free online, and they can program their own quantum computer. And it'll run. By the way, it'll run in multiple locations around the world, and they won't tell you which one.
That's
and
insane.
They can do that. If you could imagine writing A to B to C to D to E, that's the way the regular computer program would work. This is A, B, C, D, E,
all
right? Out.
Dang,
all at once.
Turbo.
So instead of a long sequence of commands to achieve an end, I can do all of the inputs at once.
Snap a finger.
Right? Because I have all the inputs in my box.
It's already in there. Oh my.
So it really is transformational. It's going to be enormously fun as a future. It's fun, I think, for students to recognize that this is the future of the 21st century. The computers today that run on the old style of logic are still going to be useful, just like cars of today are still useful. But the things that are going to be even more useful in our future, maybe it's flying cars or electric flying cars or something else, are going to be transformational in society, just like cars were transformational over horses.
Vroom, vroom, vroom. Do you know what is the best way to turn in reverse when parking on the right side? Well, before we get into this driver hack, we asked some people how they turn in reverse and park.
If you don't have a rear view camera in your car, then I highly suggest having high spatial awareness.
I don't like to park backwards because I hit the garage 3 times just going straight.
I cut my wheel as hard as I can and I go backwards really, really, really slowly. But if I'm not sure, I open my door and have a wee check just to see if I'm lined up.
Great techniques there. Let's get into our driver hack now. When reversing in a parking space on the right side, drive forward in a straight line. Align the passenger mirror with the parking space line. Turn the steering wheel full to the left. Drive forward until you see the corner of the target parking space in the side rear view mirror. Then, turn the steering wheel all the way to the right. Reverse the car until it aligns with your parking space. Straighten the wheel out and reverse. The car goes right in. This should be the most effective way to turn in and reverse, parking on the right side.
All right, I'll use that next time.
I get it now.
That makes total sense. I'd try that.
Remember to drive safely and please be courteous. I am Alan Sampson, reporting for Evolve the Earth. Now back to our show. That's a long time ago, but the pace is so rapid now.
It is.
It is so fast. And I think we're talking about implications. Did you discuss the implications of quantum entanglement?
So the whole idea of our ability to predict at the biggest scales of the universe how things work,
Right.
that's Einstein's result from general relativity. The equivalent on the smallest scale is quantum mechanics. Quantum mechanics is, although it may sound more complex, it's not science fiction, it's not theory. We've been using quantum mechanics since the 30s. It was part and parcel for our ability to do the Manhattan Project.
Right.
It's part and parcel for us to do televisions and computers and computer monitors. So it isn't a theory, it's very practical. It's a tremendously precise technique. We can measure with quantum mechanics the speeds of particles moving in magnetic fields to enormous precision. Quantum mechanics is an enormously successful theory.
Right.
Where it doesn't get us yet is at the edge of the universe, how it modifies and how it relates to gravity. And so we might talk about that as another area where understanding at the tiniest level of the universe and understanding at the biggest level of the universe, is there one encompassing idea that will take both of those? And that drives all kinds of scientists from all kinds of areas to search for, if you will, a unified theory theory that says, I can, with one set of equations that are consistent at the biggest scale of matter or at the tiniest motion of a single electron.
Wow.
That's enormously powerful and enormously thought-provoking because it forces us now to think about the universe and space in a different way.
Oh man, that's just like physics outside of Earth.
Well, you'd think of it, it's, you know, I think, oh golly, I'm talking about physics at the edge of the universe.
Yeah.
But the reality is, this is actually impacting our ability to capture this right now.
Right.
There are practical implications to our understanding that lead to advancements in science and technology that benefit us. And that's maybe one of the most important meta lessons here, is that it may sound very esoteric and may sound like this has nothing to do with, you know, getting to school today or having breakfast or, you know, maybe watching the Warriors on TV. And yet the reality is, by asking these questions, you and I and all the rest of the students are going to learn more about how nature works. And I guarantee you, as a result of that learning, things are going to be made that are going to change society.
How did the advances IBM made last year actually selling quantum computers help humanity with the medical research that they promised?
Yeah, really good question. So when we go back to my model here, where in a box, I have, you know, not just one qubit, not one black and white ball that's simultaneously both, but I put many balls in here. That was to give you in a sense that if I can entangle multiple qubits at once, not just one, but 2 or 4 or 8 or 12 or 72 as IBM has done, and as researchers in Europe are doing now, hundreds of qubits. Remember, the more qubits I have in my box, my quantum box, the more inputs I can effectively create into a problem to solve at once. Not one student schedule, 1,000, 10,000, a million students schedule, the whole world. One of the neat things that happened was that we're dealing here with what we called this black and white ball, a qubit. There are lots of things that can be used as qubits. One is an electron. An electron has this quality that we call spin. It isn't really spinning like an ice skater, but it's a convenient way for us to visualize an electron having a spin up or spin down. And that becomes then a qubit. It is both spin up and spin down in the box, in your box too. If you test it and find an up, I got an up. If you test it and find it down, I got a down. But it isn't just electrons. I can do this with light. I can do this with packages of light called photons, and photons have an arrangement or an orientation called a polarization. It's why our Polaroid dark glasses allow some light to get in but block glare. So photons can be entangled. Those are individual entities, an electron, a photon. You and I aren't made up of individual entities. You and I are made up of cells, which are made up of molecules. At the end of December of just last year, Princeton scientists have entangled molecules.
Oh, wow. What?
So a molecule is multiple atoms linked together, right, electrically. But I can now make quantum molecules.
Quantum molecules.
You and I are made up of molecules.
Whoa.
What's to say I can't use that understanding of a molecular quantum computer that now we're talking about something that has the ability to work within our body.
Wow.
See, an electron, if I want to get a quantum electron, I got to cool my experiment down to enormously cold temperature so that just the random motion, just the shaking, right, doesn't overlap my experiment.
Right.
It needs to be so cold that when you reach out, I only pull out the one thing out of this many factored qubit box. That right now requires us to super cool experiments. What happens if in our body we're not that cold? Would a quantum computer work? No, we're too warm.
Okay.
Now, understanding that molecules can become qubits, maybe we're going to get to a point where we can design a quantum computer that'll work at room temperature. Now you're talking about a complete change in how we look at what a computer can do and what kind of facility we have to use to be able to take advantage of its programming. So I have no idea. And I am sure that if there are quantum physicists and quantum engineers watching this, they're cracking up because I'm probably completely wrong. We can speculate on the process of science and say that it is very possible that these kinds of advances in science are going to lead to the elimination of disease. Elimination of, okay, you've been diagnosed with a cancerous cell.
That would be the best.
Could you then find a way to deal with chemical inputs or radiation inputs to remove the cell so that you don't even have it? It isn't remission where it's still there but not turned on. It's removal. The fastest adopter, I think, of one of IBM's quantum computing was a hospital, a research hospital. So think of like UCSF here in the Bay Area. So the University of California, San Francisco's medical research thing, which is state-of-the-art, top of the world. So a research hospital, I think this was in Pittsburgh, bought one of IBM's first quantum computers, a big multi-qubit computer, to start working on how do you do protocols for understanding disease and stuff like that. That's what's going to happen. We're going to be able to, I think in maybe 50 or 100 years, maybe it's less, we will be able to understand the progression of disease and what inputs we have to do so that we could remove it. Boy, is that going to create a tension in Earth, because we will not have the natural lifespan of humans today.
Right.
We're going to extend it because we literally can have a much longer lifespan free of disease.
Oh man, that would be amazing. I can't wait for that to happen.
It might in your lifetime.
I hope
or if
so.
you're so blessed, your kids or your grandkids.
Can we harness the power of nuclear fusion for clean energy?
Yeah, really good question. The fun thing about being here in the Bay Area where Chabot is, and our colleagues at Las Positas and Livermore, is right in the middle between the Lawrence Livermore facility and their National Ignition Facility, NIF, are doing groundbreaking work, worldwide work, in making fusion. So fusion first, to give it a sense, was, and we can actually use our same model. So fusion takes into account that in a nucleus of an atom, I'll have protons and neutrons.
Okay.
I will have particles that make up all matter. It doesn't matter whether you're made out of gold or lead, you're made out of water, you're made out of carbon. Every atom has protons and neutrons in its nucleus.
Okay.
Now, if you had two protons, if I can borrow yours, thank you, they are positively charged and would repel one another. It's like two magnets. Two north-north magnets won't get close to each other. Two positive positives won't get close to each other.
Right.
So what fusion is about is getting these guys so close to each other that they stick. So they need to be covered in a glue. And if you want to think about the glue as matter, and you use E equals mc squared, the amount of glue that they are covered in, if I can get rid of some of it, because remember, I only need to put glue on here. I don't need to put glue on both.
Okay.
If I can get them to hit, a little bit of that extra glue is not needed.
Oh, okay.
If I can turn by E equals mc squared, that little bit of glue into energy, the energy comes out. That's fusion. Fusion unites smaller things into bigger things. Now, it turns out these neutrons are really useful because the neutrons are also covered in glue.
Right.
And so it makes it easier for us to do this, right?
They're trying to get away from each other.
Right. And, or if I can borrow yours, if I can do this.
Yeah. Oh, wow.
Right. And so this is helium. So two protons and two neutrons, that makes helium. So if I can take one proton and through a series of interactions, turn it into helium, I'll get enormous amounts of energy out.
All right.
Works out to be about 0.7% of the mass of this glue that I'm talking about turns into E equals mc squared. So here's what happens as a result.
Right.
We have for 50 years been trying to do this. This is what the sun does all the time. The sun takes 7 million tons of hydrogen every second.
Wow.
And turns it into helium.
Whoa.
So
That's a big
stars,
balloon.
the stars are doing this all the time. That's why they shine so brightly. Can humans do it? Well, no. It is hecka hard to get these things to hit because they're repelling one another.
Right.
I put them under enormous temperatures and pressures to get them to move so fast they hit. What Lawrence Livermore's doing is they have 192 lasers. 192 lasers simultaneously zapping a little tiny holgram, as it's called, a little tiny gold container. The gold container has a little diamond encrusted capsule of hydrogen.
Okay.
And it's heavy hydrogen. It has a couple extra neutrons in it. And that little tiny container, and you'll see the picture of it, that little tiny container containing hydrogen zapped by 192 lasers simultaneously turns some of that hydrogen into helium, and I get energy out. Now, 2 years ago, the end of 2022, Lawrence Livermore Lab was the first place in the world to say that we got more energy out than it took to make it happen. So that was a net positive reaction. We've been doing it for years, but it always took more energy to fire the lasers than the little bit you got out. Because it's very hard to do. The instant a laser hits that little tiny bit of hydrogen, I generate a plasma, and then the other lasers hit the plasma, they don't hit the hydrogen. So it's almost as though you have to time this so perfectly that everybody's energy arrives right at exactly the same. Try to get 3 people to arrive to a meeting at once, let alone 192, and I mean they need to arrive at a nanosecond. They need to all arrive in a billionth of a second of each other for this to work. So what Lawrence Livermore has done is now getting more energy out. Now in Europe, they also, good science has done multiple places in multiple ways to reproduce experiments for validity. In Europe, they don't have the same facility as NIF that we have. They have a tokamak, which is a big magnetic container. And they've also now, just recently in the last year, been able to generate energy out at scales for the amount of hydrogen they're using that are brand new, that we're chipping away at this, eventually being able to run fusion for ourselves and get energy out. And your question was, what impact and what implication does this have for our future? Well, since hydrogen is the basis of water, H2O has lots of hydrogen in it. If I could take a cup of water, there's enough hydrogen in the water that if I could fuse it into helium, I could power Hayward for a year.
Whoa!
Remember what the outcome of this was? Was helium. What do you do with the helium? You put it in a balloon for a party. It's not toxic, right? It doesn't pollute the environment. It's not something that we need to worry about and sequester and put away. In other words, fusion not only produces energy, it produces a non-toxic output as the endpoint. As opposed to today, if you use fission, which is big nuclei, uranium and thorium and plutonium, and split them apart, the little tiny bits left over are still radioactive. And I have to bury those, and those create enormous political and sociological and physical problems for the rest of the world. If I bury something that's radioactive for 50,000 years, I have polluted the area around it. You don't want it to be near groundwater, you don't want it near people. What does it do to biota? What is it going to do for 30 years down the road? Fusion has the possibility of not only powering our planet, but powering it in a way that is not going to generate a negative reaction. So it is worth our investment, but it is a heck of a hard problem to work on.
We better work on that problem now.
And that's why students are taking physics, that's why students are taking engineering. That's what Lawrence Livermore Lab, it's one of the most exciting places to be because literally you are transforming the world.
And that's where we'll leave things for now, but the story's far from over. Join us next time as we dive deeper into outer space. Trust me, you won't want to miss what happens next. You are tuned into Evolve the Earth Talk Show podcast. Like, follow, and subscribe on all platforms at ETE Talk Show. Leave a comment about any subjects you would like us to discuss or questions that we could answer during our show. Thank you, world. Your time is highly appreciated. I'm your host, Alan Sampson. See you all on the next show.